Acceleration. The concept of acceleration is defined as follows. I will use the letter A. Now the nice thing about this functional form is that it looks very similar to what we've seen before, which was velocity. The velocity was defined as the change of position over change of time. The acceleration is defined as the change of velocity divided by the change of time, which means that whenever you're going to have a non-zero acceleration, you must change your velocity. That's it. So whenever the velocity is constant, the change is zero. If the velocity is constant, you don't change your velocity. Therefore, the change is zero. Therefore, the acceleration is zero. Every time there's going to be a change of velocity, this will imply a non-zero acceleration. The same way as v was a vector, the acceleration a is a vector. Delta v has the units of meters per second. We're going to divide this by delta t, which has units of seconds. Therefore, the units of acceleration is meters per second divided by second, which is meters per second times second, or meters per second squared. Now we need to be very careful about what this means. Remember that the velocity is a vector. Therefore, it has magnitude and a direction. So when we say that there must be a change of velocity for an acceleration to be present, we mean there must be a change of its magnitude or a change of its direction. Meaning, if you're traveling with a constant velocity v in this direction, then at some point you're going to increase your speed, but you keep the same direction. Between this point and this point, or t1 and t2, since the velocity magnitude has changed, there must be an acceleration that caused this to happen. No problem. Now, let's imagine that you're traveling with a particular velocity in this direction and this particular speed. And then you're going to change the direction of this vector, but you're going to keep the magnitude constant. Therefore, the magnitude of this new vector, v, is the same as the magnitude of the original vector, v prime is the same as the speed, v. So they have the same speed, v and v prime. The only difference between those two vectors is the direction. This one is towards the x. This one has a particular angle. So in this particular case, we haven't changed the magnitude, but we have changed the direction. For this to occur, there must be an acceleration present. So an acceleration is non-zero if either the magnitude or the direction or both are being altered. Keep this in mind because this case will come back to us in circular motion. The same way as we have rewritten this so that it looks like a line, and we had x is equal to x initial plus v t minus initial, and we decided to set the time is equal to 0, initial is equal to 0, so we had x equal to vt. We can do the exact same thing with acceleration. Let's consider v initial and t initial to be the center of our coordinate system. So initially we start at rest, therefore this is 0, and we start counter at t is equal to 0. Therefore we have a is equal to vf over delta t, which can be written as a is equal to v over t. I'm going to drop the vector notation and consider a scalar case. I'm going to multiply both sides by t, and I end up with v is equal to at. So I'm doing the exact same thing as what I've done with velocity. And again, I'm going to write the line equation right below it. And I can see clearly that now instead of plotting y versus x, I'm going to plot a physical concept, and I'm going to replace my y, or my dependent variable, with the velocity. And I'm going to plot as my independent variable the time. And notice very clearly that this must look like a straight line, and the slope is given by, or will tell me something about, the acceleration. So the same way as the slope was giving us information about the speed and the velocity in the x versus t diagram, if now we're dealing with a v versus t diagram, similar analogy, because the functional forms are the same, the slope will tell us some information about the acceleration. If we have a positive slope, positive acceleration. If we have a negative slope, negative acceleration, which we call deceleration, which means we're going slower and slower and slower. Our velocity from this point, whoops, to this point, went from this value to this value. Therefore, we are decelerating. If the velocity goes from this value to this value, obviously it increases, and therefore we're accelerating. So the sign of the acceleration doesn't tell us anything about the direction. It tells us whether we're going faster or slower. But the way that we're going to analyze those v versus t graph are going to be exactly the same method, following the same methods as when we use to analyze x versus t diagram. The same way as we took the limit as t going towards 0, we can do the same thing with acceleration. So really, when we use delta t and delta v, we're considering big interval. This is known as the average acceleration. And if we start taking the limit as delta t goes to 0, therefore we're considering smaller and smaller and smaller interval. This will give us the instantaneous acceleration, which is dv over dt, which is the value of the acceleration at specific instant of time. So again, if we have now a v versus t diagram, and we have a straight line, we know that the acceleration is constant, which means that we're changing our velocity at constant rate. The change from here to here is the same as the change from here to here is the same as the change from here to here. Which means that if you were in a car and you're pressing on the acceleration pedal, you're pressing it with a constant rate. If you don't change the pressure on the pedal and you cruise at the constant velocity, that would be something like this. If you start pressing on that pedal at a constant rate, that means you press with the same amount of force per same unit of time, then you will change your velocity at the same rate. You would expect a straight line. If now you start to increase your velocity faster and faster and faster with time, that means the acceleration gets bigger and bigger and bigger. We have a non-constant acceleration. In this particular class, we will be dealing with constant acceleration only, which means that v versus t diagram will only have a straight line present.